I'll start the recording. Okay, this week we're going to talk about virtual memory management. Last week we talked about paging and segmentation, and now we're going to take it a step further, where we're going to be creating ways of managing memory so that the entire user's process does not have to be in memory all at the same time. Parts of it will be swapped in and out of memory onto disk. Before we talk about that, though, I do want to go over the homework from last week. I know a lot of you just handed it in yesterday, and I don't have it graded. I didn't even get a chance to look at most of them. But this was your first problem, and it talked about programs being structured with the code segment, followed by the data segment, followed by the program variables. There's a stack allocated and a heap, and as the program executes, the stack and the heap will grow. The stack is used for various purposes, like when you call a method, it pushes certain things onto the stack, and then those things get popped off the stack when you return from the method, and so forth. And then the heap is actually the memory space that's being used in your program. So what I wanted you to do in this question is talk about contiguous memory allocation, pure segmentation, and pure paging, and kind of look at what happens as that heap grows or as the program executes. Because the program actually takes up more storage as it executes than when it initially starts to run. So that's kind of what we were looking at in this exercise. So here we have contiguous memory allocation, and this is just a picture of what a program would look like in memory. We have the code, we have the data, then we have the heap and the stack, and the heap and the stack are growing toward each other in the free space that's kind of in the middle of this memory that is allocated to this process. So if you think about it, what does that mean as your program executes? Well, if the heap is growing and the stack is growing, if you didn't leave enough space in the middle when you allocated the whole amount of memory for this process, eventually the heap and the stack are going to grow right into each other, and you're going to run out of memory. So the kind of answer I was looking for here is that with contiguous memory allocation, the entire amount of memory must be allocated to a program before it starts running. So the whole thing is put into memory as one big block of memory with free space, with kind of a hole in the middle where your stack and your heap is going to grow. So enough memory must be available for the stack and the heap to grow as the program runs. If enough memory hasn't been allocated, it's possible that the entire program will have to be relocated to a larger space in memory so that you can get more space within the middle of the allocated space so that your stack and heap could grow more, or the program can fail with an out-of-memory exception. Okay, so with contiguous memory allocation, we're allocating a fixed amount of memory before the program even starts. So if the program's stack and heap grows too much, you're going to run out of memory. Okay, and that's kind of what I was looking for in that question. Are there any questions on that one? Okay, so now let's look at pure segmentation. And again, I have a picture here taken from your book of segmentation. With segmentation, your program is divided into segments. So these different things like the stack and the heap and the code and different parts of the code are actually allocated to different segments in logical memory. So your logical address space matches kind of how you think of your program. If you think of a program in Java, you have variables and you have methods and you have Java libraries that you're linked to and so forth. What segmentation does, okay, Aida saying some students are having problems with access to the site. Are they just not able to get in? Are they having problems accessing Blackboard in general, or just this site? Just the Blackboard Collaborate. Do you know, Aida? They can't get to Blackboard at all. They can't get into the course. Oh dear. Well, there's really not anything I can do about that. It's good to know, and what we'll have to do is hope that they're able to get in, and they'll have to review this part of the recording. This is all being recorded, so they'll just have to review the recording when they are able. I've been able to get into the site this morning, and apparently all of you have. Yeah, that's good to know. I was kind of wondering why there were so few people in the course today. I didn't know if there was, something else going on. So thank you for letting me know. Okay, we were talking about pure segmentation, and like I said, with segmentation, a program is divided into segments. And then what happens is that each of these segments can be allocated to the physical memory, or can have the physical memory allocated to it that it needs. Okay, so one of the segments is going to be the stack. So as the stack grows, all that means is that the amount of memory that segment has is going to grow, and it's not going to affect the other parts of the program. So unlike contiguous allocation, where we allocated one big block of contiguous memory for the program, with pure segmentation, these different segments of a program are going to be scattered throughout memory. And so if the heap or the stack needs to grow, that's not really a problem. Okay, so do you see the difference there between the pure segmentation and the contiguous memory allocation? You can see that there's an advantage here with the pure segmentation. Any questions on that one? Okay, then let's go on to pure paging. Now with pure paging, a page table is used to map all the program's virtual address spaces to a physical frame. And again, I took a picture out of your book that illustrated it, but then I tried to explain why, why that is a good idea when you have a heap and a stack that's growing. So what's going to happen is all the frames that are needed for the heap and stack are not necessarily going to be allocated initially. Instead, we can just allocate those entries in the page table for however big we're going to let the heap and the stack grow. And then as it grows, that's when it would go out and try to find an available frame in physical memory. So again, with pure paging, the actual physical frames do not need to be allocated initially. You do need to allocate everything in the page table, but then we only will allocate a new frame in the physical memory when the heap and stack grows enough that it needs more frames than whatever was initially allocated. Okay, so that's the difference with paging. So paging actually gives us even more flexibility than segmentation. And what you're going to see is when we talk about some of the things in this week's lecture, what most operating systems actually do is kind of a combination of paging and segmentation, where we're loading different pages in and out, and so our virtual address space is going to be different than our physical address space. But all the things that we're talking about in week 9 kind of build on some of these ideas in week 8. So that's kind of what I was looking for. Just as your program grows, and the things that grow in a program are the heap and the stack, as your program grows, what do these different memory allocation schemes do for us or not do for us? Okay, so you could see that contiguous allocation kind of was the most restrictive, and then segmentation gave us some more flexibility, and then paging gives us even more flexibility than just pure segmentation. The next question was a question about converting logical addresses to physical addresses using a page table. So we have a computer system with a 32-bit logical address and a 4K page size. The system supports up to 512 megabytes of physical memory. How many entries are in each of the following? And we want to look at a conventional page, a single-level page table, and an inverted page table. And remember, with the conventional table, what you're doing is you are allocating the page table with the page numbers, but you may not have actual physical frames allocated to those logical pages yet. An inverted page table does it the other way around. It lists all the frames that are available in the system, and then just puts what pages are using that frame. So let's take a look at this and start with the conventional single page table. We were told that the address is a 32-bit address. And welcome everyone who's just joining us. I do understand that there was a problem getting into the system. It looks like some of you are getting in now. What you're just going to need to do is look over the beginning of the recording, because everything's being recorded up to this point, and you can kind of get caught up. Where basically what I've done so far is just go through the first homework problem, and we're starting on the second homework problem at this time. So again, we were told in the problem that the addresses were 32 bits. Okay, so we had a 32-bit logical address. So I know that, and this was a picture that I took just from your book, I know that M is 32 bits. So this whole address space, this whole thing is 32 bits. Now the other thing that I was told in the problem is that we have a 4K page size. So 4K is 4,096 bytes. So 4K can be addressed in basically 12 bits, FFF. Okay? So from what I was told, FFF, if you know hexadecimal, and you should have learned hexadecimal in one of your earlier computer science classes, FFF is equivalent to 4,095, 12 bits. So what I have here then is part of my logical address is going to be the offset, okay? And that's 12 bits. So what I need to figure out, if I know the offset is 12 bits and the overall length of a logical address is 32 bits, then how many bits do I have left over for the page number? Because how big the page number is going to tell me how many entries I can put in my page table. It can only be as big as the largest page number. So to figure that out, all I do is I take M, which is 32, I subtract off N, which is 12, and that gives me 20. So I have 20 bits that I can use to store the page number. Okay, and again, this came up again in your programming assignment with this 32-bit address, and 12 bits were for the offset and the other 20 bits were for the page number. So the number of entries, or the number of page numbers I can possibly have, is 2 to the 20th power. And that's the answer for that one. Any questions on that? Do you understand this structure here and how I used it to get that number? Okay, so it was easy according to Aida. It's always easy once you see the answer, right? Okay. Now the next thing was an inverted page table. With an inverted page table, what was important to realize is that the page table has one entry per frame. So we were told that physical memory is 512 megabytes. A page size is 400 kilobytes. So physical memory is about 512 million bytes. The page size is about 4,000 bytes. So I just do the division and say if I have 512 megabytes, I divide it by 4 kilobytes, and I get 128 kilobytes. So the number of entries is approximately 128,000 entries in my page table. Okay? Any questions on that? Now you can see with this we had a 32-bit address space. The page table in our first example was much smaller than what we have with an inverted page table. That's why the inverted page table is only used when you have very large address spaces like 64 bits, because we wouldn't be able to fit the whole page table in memory. So we use an inverted page table in those cases, because then the actual number of frames is smaller than the overall virtual address space. Okay, so that's how that question worked. Any questions on that? Okay, now the last exercise was a programming exercise, but I tried to make it as easy as possible for you by writing most of the code for this exercise. Some of you didn't figure out what you needed to do, but I did send you a PDF. I actually sent it twice because some people didn't see it the first time, and that was the day we were having all those problems with getting into Blackboard and getting into our emails and everything. So I resent it, and basically all you needed to do was write the convertAddr method. Now, this problem is making the same assumptions that problem 8.16 made. You have a 32-bit virtual address and a 4K page size. So it's the same assumptions that we made in the last exercise. And we already looked at with a conventional table how you would convert that, which bits are the page number and which bits are the offset in that address. And that's all we wanted to do in this exercise, is take a 32-bit address and split it into the page number and the page offset. Now your book said to use an unsigned 32-bit integer. Java doesn't have an unsigned 32-bit integer, so we are using a long, which is a 64-bit integer, and just know that the address is going to be stored in the rightmost 4 bytes. Okay, so since Java doesn't have an unsigned 32-bit integer. They're actually supposed to be getting that in the next version of Java, but they don't have it right now. We're going to use a long for our address because we want to be able to use all 32 bits in the address, where if you remember from your earlier computer science classes, usually that high order bit is used to determine whether a number is positive or negative, but with an unsigned number, that bit is just a bit. So that's why we want to use a long so that we can manipulate that lower 32 bits without it interpreting that high order bit as the sign bit in the value. Okay, so that's just a bit of a background why I chose a long for the address. Okay, we want the test program, and I gave you the test program to give this output. This first one was the example that was in your book. So if you were given an address of 19,986, the page number is 4 and the offset is 3,602. Okay? And if you're given a page number or an address of 0, obviously that's going to be at the very beginning of our address space. Munira, we know that there was a problem with Blackboard, and so I understand people are entering late. You'll just have to watch the beginning of the recording to get caught up to this point. Okay? So what we wanted to do in this problem is pretty much take any address and convert it into that page number and offset. Now there were actually 2 ways of doing this. When I first looked at this problem, I looked at this and said, okay, the address is 19,986. I need to figure out the page number. Well, I know that memory is divided into 4K pages, so I took 19,986, divided it by 4,096, which is 4K, and I came up with a page number of 4 and an offset, or a remainder, if you're doing the division, of 3,602. Right? Does that make sense? Does everybody see how you can use division to work this problem? In your book, it talked about how you go from a page number and an offset to the physical address. We're just doing it in the opposite direction. So if I take 4, the page number, and I multiply it by the number of bytes in a page, which is 4,096, and I add 3,602 to it, I will get 19,986. Okay? We're just going in the reverse direction. We're going to do a division and then get the remainder. Does everybody see what I'm saying here? Okay, because there was quite a bit of confusion on what needed to be done here. And it really what could have been a very simple division problem. Remember that your page numbers start at 0, your offsets start at 0. So the first physical page in memory is page number 0. The second physical page number in memory is page 1. So if I have an address that's 4,096, it's in the second page in memory, which is page number 1, offset 0. And then here, this number here is actually the largest number I can get in 32 bits. And so that turns out to be page number 1,048,575 with an offset of 4,096. So all of this, these addresses were already in the test program. All you had to do is write the convertAddr program. And it was a 2-line piece of code. You had to write 2 lines of code for this. First, take the address and divide it by 4,096 to get your page number. Okay, I'm doing integer division. So I'm dividing a long by an integer, and the result I have, I'm going to cast to an integer because my page number is an integer. Okay, so I just took the long address that was passed into my method and I divided it by 4096, and that gave me the page number. So anything between 0 and 4095 would give me a page number of 0. Anything between 4096 and 8191 would give me a page number of 1, and so forth. I'm doing simple integer division. The other thing I need to do is get the remainder to get the offset. The way I get the remainder is by using the mod operation. And again, I just take this long address and do the mod of it with 4096, and that gives me the remainder, which gives me the offset. So I'm just doing a simple division problem and keeping the remainder. So that was actually the simplest way to solve this problem. Any questions on that? Okay, you want to submit the project after the midterm. You're talking about the threading project, Arwa? The problem I have with you submitting the threading project after the midterm is that you're assigned another project this week. Okay, and so if you wait until week 8 to do your first project, you're only going to have 2 weeks to do your next project, which is going to be very difficult to get it done in those 2 weeks. So no, you can't submit your project after the midterm. Okay, I'm sorry to break your heart. But what I could tell you is, to me, I know you guys don't have a lot of, or some of you don't have a lot of Java coding experience. If you put in, start working on your project and submit as much as you can, and the parts that you couldn't figure out, make sure you just put comments in there to say, what I was going to do here is create a thread and, get the semaphore and whatever else it was that you were going to do in that project, okay? Because I will look at the logic that you write in your code and give you credit for what you got done, not just whether or not the whole thing worked. Okay, so I'm going to ask you to submit your code to me for the project by the deadline. But if you didn't get it working, make sure you at least tell me in your comments what you expected to do. And if you have code that doesn't compile or isn't working, you can even leave the code in there and comment it out and say, this wouldn't compile, so I can at least see how far you got, and I will give you partial credit. Sarah, a lot of people had problems getting into the class, so you're just going to have to look at the recording. Okay. I need to move on here because we only have a half hour left and we haven't even gotten into the material for this week. Okay, the other thing I wanted to show you was another way to do it, and I was actually happy to see that at least one of you who handed in the assignment early did it this way. What this does, this is again another implementation of the convertAddr, and all it's doing is it's doing a shift and a mask of the bits in the address. So remember, the page number is the high order 20 bits of the address, and the page offset is the low order 12 bits. You can shift bits in Java. Okay, this is hexadecimal. You guys should be familiar with hexadecimal. Remember, the low order 12 bits are what I want for the offset. So FFF is 12 bits turned on in hexadecimal. Okay. So what I'm doing here is I'm taking the entire address that I have here and I'm shifting it. And I'm shifting it in this direction, 12 bits. So what's going to happen is the 12 bits of the page offset are going to actually fall off the end here. Those 12 bits are going to fall off the end over, out of this 32 bits. And what I'm going to be left with is those other 20 bits shifted all the way down in the address, and that will be my page number, because that's the 20 bits. What's going to be left is the 20 bits that now have been shifted over by 12 bits, so it'll be shifted over. And so the page number will now be in this 20 bits of my address space, and I get the page number. The other thing I could do is start with the initial address and just mask off to get the offset. Now what a mask does, here, let me clear my page here. What a mask does is it does an operation where we're actually doing an AND. Okay, we're doing an AND operation. Whoops, let me get my marker back again. We're doing an AND operation. And you can see it right here. And so what it's going to do is take the 64 bits in the address and do a logical AND with these bits. So any bit that is in these last 12 bits will be retained. So because a 1 and a 1 will give you a 1 when you AND them together. And again, I'm just doing bit manipulation. And all the other bits are going to be 0 in my mask. So the page number is going to effectively get zeroed out, whatever was there. And I'm only going to retain the 12 bits that were in this part of the address. Okay, so I didn't really expect anybody to come up with this answer, although some of you did. One of the reasons why you would use shifting and masking instead of division is that the CPU can do shifting and masking very, very quickly, whereas doing a division and a mod is a much slower operation. So if you have to do this for every single address, logical address that you have in an operating system environment, you want to do it as fast as possible. And this solution is faster than the division solution, but they both work. Okay, so I just wanted to show you that. Okay. Now to get into what we're doing for this week, we're going to be talking about virtual memory systems. We're going to look at demand paging, the working model, the working set model. Your book goes into shared memory and memory map files, and as well as how the kernel is managed. I'm going to focus mostly on demand paging and page replacement algorithms because that's what all your homework assignment is about. That's really the main points in this chapter, and everything else is kind of related to that. So you need to understand about demand paging. As you might recall, a program has to be retrieved from disk and placed into memory in order to run. The other algorithms that we looked at in the last chapter, for the most part, they required the entire process to be in memory in order for it to be run. The only exception was when we looked at dynamic loading, where we had some code remaining on disk and then loaded in as needed. With virtual memory, we're going to be able to execute a program even though the entire program is not in main memory. Basically, what we're going to do is only put into main memory the parts that we need, because some parts of the program will never be used. For instance, sometimes you have error handling in your program. An exception happens and you need to handle it. That error handling code you might want to just leave out on disk and not put in main memory, because main memory is a precious resource. You don't want to use it all up. So you just load it in when it's needed. Some large data structures, arrays and so forth, a lot of times you allocate more than you need, So why allocate all those frames when you might only be using a portion of the frames? And then there's some routines or some methods that you might be using in your code that aren't going to be used. What we want to do basically is separate how we think about our logical memory from our physical memory by allowing not everything in the logical memory to be mapped to physical memory at the same time. Some of it's going to be swapped in and out. So only part of the program needs to be in memory for execution. The logical address space is going to be bigger than this physical address space. And it gives us a number of advantages, like allowing address spaces to be shared, allowing process creation to be more efficient because you don't have to allocate all this memory right up front. You can have more programs in memory running at the same time. And if you're swapping out a process, you really only have to swap out those frames that that process is actually using. So we're going to look at some ways that we can manage a virtual memory space. Okay, and this just gives you a nice picture of what happens with virtual memory versus the physical memory. We still have our logical memory or our virtual memory that's mapped to physical memory, but everything in logical memory isn't necessarily in the physical memory. Some of it's out on disk, and if the program accesses something, okay, like, you know, this example right here, whatever it's accessing right here in virtual memory, it looks and it tries to access it in physical memory. It's not really in physical memory. It might swap out a page or a frame that's already in physical memory, put that back out on disk, and swap a new frame in that was needed by the program. So basically all we're doing is swapping frames in and out of disk, and we're allowing the logical memory, or the virtual memory as we're calling it now, to be greater than what we have in physical memory because we can swap in and out the frames from the disk as we need them. So we have what's called demand paging. And demand paging is what I was just talking about, where we're just loading pages as they're needed. So it's like a paging system that we talked about last week, but it also includes swapping. Okay, so what we have here is like I showed you before, we have our logical memory, we have our page table, we have some of our pages loaded into physical memory, but some of them are still on disk. Okay, so with pure swapping, the entire process was being moved to and from disk. With paging, individual pages can be moved to and from disk. So we're really swapping out just pages rather than processes. So what happens here is the pager kind of guesses what pages are going to be needed and loads them into physical memory, and then indicates in our page table that the pages are valid. When they're not valid, it might mean that it's a true memory error. You're trying to access something that your page doesn't, or your process doesn't own. But it also might mean that the page that you want to access just isn't in physical memory at this time. Whenever the system has to go out to the disk and bring a new page into physical memory, that's called a page fault. Okay, so here's what happens when a page fault occurs. Usually what's going to happen is there's a check to see whether the reference was valid or not valid. Okay, which I just mentioned that to you. It's going to check to see whether you're allowed to access that memory or the memory just needs a page loaded into it. If it's a truly invalid memory access, your process would be terminated. You were trying to access a page that your process didn't own. Okay? If it's a valid address, but it's simply not in memory at this time, what would happen is a trap would occur, okay? An exception would occur, and that interrupt would be trapped. It would go to the operating system and say, okay, we need to get this page from our backing store, from the disk. Okay? So it would find that page out on disk, find a free frame in our physical memory, and read that page into the frame. It would then go back and update the page table to say there's now a valid page in memory, and then it has to go back to the process and reset that process to try the instruction again. Whatever the instruction was that needed to load something that wasn't in memory, it went through this whole sequence to get it in memory. Now it has to go back and say, retry that. So it's important to note that the instructions have to be restarted after there's a page fault. Because when the page fault occurs, there's a context switch. Remember way back when we talked about context switches and things getting swapped out of memory or moved out of memory, and the state of the process gets swapped out and the new process gets swapped in? Well, that's what's happening here. Now when the process gets swapped back in and is ready to run again, we have to go back and rerun the instruction that caused the page fault in the first place. Okay? Now this wasn't a problem with non-demand paging, which is what we talked about in Chapter 8, because all our pages were in memory. We weren't having page faults. A performance goal when you're doing a page fault is, when you're doing this type of paging, is to actually reduce the number of page faults. So the different algorithms that we're going to look at for paging, we're going to look at how many page faults are created, because that's important. The more times it has to go through this whole process to handle a page fault, the slower your code is going to run. So a lot of what the rest of your chapter talks about is how to reduce the number of page faults. The number of page faults is dependent on what page replacement algorithm you use. When page replacement is when a page needs to be brought into memory and there's no free frame available. What you need to do is find a page in memory that's not being used, swap it out to disk, or page it out as they say, and bring the desired page into memory. So again, we want an algorithm that results in the minimum number of page faults. Okay, does everybody understand what a page fault is? Any questions on that? It's just swapping these pages in and out from disk as they're needed. Okay, your homework for this week is about paging. And so you have to do exercise 9.9 and take the exercise from the book, because I wasn't able to copy and paste the table for some reason from the book. I just kept getting a big black square. So I actually typed this whole table in, so I might have made some mistakes. So just make sure that you use the table that's in your book and not what I have on this slide. And here now we have a 16-bit address. The other homework problems that we had, we were using a 32-bit address. Here we're using a 16-bit address, but we still have 4K pages. The reference bit, which is here, is set to 1 when the page has been referenced, and periodically a thread will clear out the values of the reference bit to kind of indicate pages aren't being used anymore. When there's a dash for the frame, it indicates that the page is not in memory. So here, like page 12 is not in memory yet. The page replacement algorithm is a localized LRU, least recently used, and all the numbers here are provided in decimal. Okay, so that kind of gives you the setup for this problem. Now the first part of the question is to convert the following virtual addresses, and again it's showing the addresses in hexadecimal, to the equivalent physical address. So you're going to break it up, the address, into the page number and the offset. Remember now we're only talking about a 16-bit address, so the first part is the page number, and then the next 12 bits are the offset. Using the page table that I showed you on the previous slide, come up with the physical address for that particular logical address. And I want you to explain how you came up with the answer. And basically, you know, something like this. I looked up E in the page table, I got the physical address, I added the offset to it, and that's how I came up with the answer. Okay, Sarah's asking what LRU is. You should know that from your reading, but I will be talking about that during this lecture as well. I just wanted to make sure that we talked about the homework problems before we ran out of time. Okay, so I'll get to that, Sarah. It's least recently used algorithm. Okay, so does everybody understand what you need to do for part 1 of this exercise? Okay, we're just, once again, converting logical addresses to physical addresses. Okay, the second part is using the above addresses as a guide. Provide an example of a logical address that will result in a page fault. In other words, give me a hexadecimal number or a decimal number. Well, I guess they asked here for a hexadecimal one. It's actually easier to do it in hexadecimal. Give me a logical address in hexadecimal that will result in a page fault. Okay, so give me a logical address where it'll look in the page table and determine that the page is not in memory and it's going to have to load the page into memory. Okay, I just need one example. Explain why the logical address you gave me would result in a page fault. And then finally, from what set of page frames will the LRU page replacement algorithm choose in resolving a page fault? Okay, so what will it look at in our page table? Which frames will it look at to determine what pages it can use to resolve a page fault? In other words, what pages can be moved out of memory so that a new page can be brought into memory? Okay, and just explain how you came up with that answer. Okay, if you just give me an answer and not an explanation, you will not get full credit for this problem. Okay, the next exercise is also a page replacement algorithm question, and it says discuss situations in which the most frequently used page replacement algorithm generates few page faults than the least recently used page replacement algorithm, and then discuss the opposite. In what cases would the least recently used algorithm generate fewer page faults than the most frequently used? So I want you to tell me it in both directions. And all I want here is I want you to give me an example of a page reference string, which we haven't talked about, but it talks about it in your book, that would cause the MFU algorithm to generate fewer page faults, and then show me another one where the LRU would give me the fewer page faults. Okay, so that's what I'm looking for here. And, you know, explain it. You know, show me how you figured out how many page faults for each of these. Okay, so that's your next problem. And then the last problem that was assigned is your new programming problem. And this is due April 6th. So you're going to write a program that implements FIFO, LRU, and optimal page replacement algorithms presented in this chapter, and I'm going to be talking about these. The first generate a random page reference string where the page numbers range from 0 to 9, apply the page reference string to each algorithm, and record the number of page faults. Okay? So that's basically what you're going to be doing. We're going to go through some exercises right now in class where we're going to look at the page faults. You're going to then take what we did in class and implement it as a Java program, is basically what you're going to be asked to do. So those are your homework problems, and you do have some time, so we'll have more time to discuss the programming problem as we go along. But I wanted to make sure that you understood what you were expected to do in the program, in the problems for this week. And basically, it requires that you understand, again, the logical to physical mapping, and you understand page faults. To that end, let's talk about how to do FIFO page replacement. What I have here, across the top here, is what was called the replacement page string. These are the numbers of the pages that want to come into memory in a process. Okay, so page 7, then page 2, then page 3, then page 1, then page 2, then page 5, then page 3, and so forth. So we have 20 different pages here that need to come into memory in this order. So what you need to figure out is how are they going to come into memory, and which ones will cause a page fault. So let's start here with number 7, and can you tell me, is it in memory already? We have 3 frames in memory. Okay, that's what these 3 rows are. These are our frames in memory. So we have 3 frames in memory. Is page 7 in memory at this time? The program just started up. No, it's not. So what we need to do is put page 7 in memory. Was that a page fault? Yes. Okay, so that was a page fault. So what I'm going to do is I'm going to highlight my page faults so I can keep track of them. So now number 2 wants to come into memory. So we already have, let's see here, we already have 7 in memory. Ooh, my 7 was big now. And we want to put 2 in memory. So we have an open slot, so we'll put 2 in memory, and that's another page fault. Okay, easy so far, right? We have pages coming into memory, and we have wrong thing here. We have pages coming into memory, and we have page faults occurring. Page 3 wants to come into memory now, and so we already have page 7 in memory, page 2 in memory, and now we're going to put page 3 in memory. So let me just fill these in again here. We have 7, we have 2 already in memory, and now 3 wants to come in memory, and that's going to cause another page fault. Well, now our memory is full. We have 3 pages in memory, 3 page faults occurred. But now page number 1 wants to come into memory, so what do we have to do? This is a first in, first out page replacement algorithm. So what we want to do is replace the oldest page in memory. So Hala has it exactly right. and RWA does too. We want to remove 7 and replace it with 1. So now we're going to put page 1 in memory, followed by, let's put it up here, page 1. And then we still have page 2 and page 3 in memory. This is hard to do with these tools. And now, did page 1 cause a page fault? Yes. Okay. Page 1 caused a page fault. Now we want to put page 2 in memory, but page 2 is already in there. So there's no page fault here. These 3 frames will not cause a page fault. Okay, so we still have page 1, 2, and 3 in memory. Now what happens when we get to page 5? Will that cause a page fault? Okay, Hala says yes. Does everybody agree with her? Okay. Hala says yes, and we should remove 2. So now 1 stays in memory, 3 stays in memory, but now we're going to replace 2 with 5. And that caused another page fault. Okay, so does everybody see how this works? Okay. When we get to 3 here, when 3 wants to come into memory, Sarah, we wouldn't have to remove it. It's already there. We don't have to do anything. It would just use page 3 that's already in memory. Okay, so in our next iteration here, 1 would remain in memory, 5 would remain in memory, 3 would remain in memory, and there's no page fault. Now we want to bring page 4 into memory, and again I'm going back up to the top row here. I want to bring 4 into memory. Now which one do we replace? Now we replace 3. That's correct, Hala. So 4 is going to be there, 5 is going to stay where it is, and 1 is going to stay where it is. When we get to number 6, page 6, which one gets replaced next? Which one has been in memory the longest? And again, it's 1. So then we have 6, 5, and 4. And again, I have to mark my page fault so I keep track of which ones caused a page fault. So here I had no page fault, here I had a page fault, and here I had a page fault. So you should be able to complete the remainder of this on your own, and then just count up the number of page faults and tell me how many you came up with. Okay, does everybody see what we're doing here? That is the FIFO page replacement algorithm. The next algorithm is the optimal page replacement. In this one, we're going to want to replace a page that's not going to be used in the near future. So I'm going to start here by putting in those first couple of pages that we already know create page faults, just like they did. I should have filled these in ahead of time. I didn't think of that. But for the first 3 iterations, the first 3 pages will come into memory, okay? Nothing changes from our other algorithm. And those first 3 pages all cause page faults. Whoops. Get this. So that caused a page fault, that caused a page fault, that caused a page fault. Now, here's where it gets different, where it's different. We now want to look at putting page 1 in memory. And what we want to do is replace a page that's not going to be used in the near future. I know it's 11 o'clock. I'm going to continue through these page replacement algorithms. I'm going to continue talking through them so you can work on these. I did send you a PDF with these tables so you could fill these out on your own. You should have gotten that PDF with the announcement of this session. I'm going to continue through the optimal page replacement and the LRU page replacement so that you'll have the lecture that goes along with it, because we're out of time for today. If you want to stay, that's great. If you need to leave, just feel free to leave. Okay, now we're looking at what page do we want to replace when we want to bring in page 1. Our choices are page 7, page 2, and page 3. So what we're going to do is look in memory, or look ahead rather, to see what other pages are going to be used. When is 7 going to be used again? When is 3 going to be used again? And when is 2 going to be used again? And when is 3 going to be used again? Let me state that again. We want to look at when is 7 going to be used again? I'm trying to go fast and my mouth is ahead of my brain. When will 2 be used again? And when will 3 be used again? Well, it looks like 2 is going to be used again right away. 3 will be used again after that. And 7 won't be used for a long time. So I'm actually looking in the future to see which page am I not going to need to use for a while. And so what I would determine is that page 7 would need to be replaced. Okay? Does everybody see that? I wanted to bring 1 in, and I looked ahead and saw that 2 is going to be used right away, 3 is going to be used a little bit later, but it's going to be a long time before I need page 7 again. So since I only have 3 pages in memory, I'm going to choose to replace page 7 now with page 1. And 2 and 3 remain in memory. Okay, any questions on that? You see how I chose which page here? I'm trying to make it optimal. I'm trying to not swap out something or page out something that I'm going to need right away. Okay, so now page 2 needs to be used, but I already have page 2 in memory. So I don't need to do anything. So you could already see here that because I left page 2 in memory, no page fault is going to occur. Okay, now we come to page 5. Okay, so Hala asks, so the operating system will check memory and guess which page will not be used. That's the problem with optimal page replacement. It's very difficult to figure out which pages are going to be used in the future. Because when you think about your code has if-else statements, and it's doing all kinds of things. And it's very hard for the operating system to figure out what it's going to need in the future. So that's a disadvantage of this algorithm. So this algorithm really isn't used in practice. In other words, an operating system does not implement this particular algorithm, but it's used to determine how good are the other algorithms, because we compare the other algorithms to this one. In other words, when we do a first-in, first-out page replacement algorithm, we'll compare the number of page faults it gets to the number of optimal page faults, or the page replacements that were done with an optimal page replacement, and determine how close is FIFO to being as good as optimal would be. Okay? So Hala asks, so depending on what it will decide, which page will get replaced. Yeah, it doesn't know. Like I said, Hala, usually operating systems do not actually implement this algorithm. Okay, it's usually a least recently used or a FIFO or some other algorithms, and we'll see there's a number of them. But when you're looking at kind of what your operating system's workload usually is, the types of programs that an operating system usually runs, we can kind of look at what are the patterns of pages that go in and out of memory, and from those patterns decide whether a least recently used or a FIFO or a most frequently used or a least frequently used algorithm is going to come as close as optimal. Optimal means that we're always replacing the page that we're going to need, the latest. We're not going to be needing it in the near future. Okay, so what usually is done is they look at past history for an operating. They could look at past history when they're developing an operating system and say, okay, here's what my page reference string looked like in the past history. So let me calculate what a FIFO algorithm will give me in page faults, what an optimal algorithm will give me in page faults, and what a LRU algorithm will give me in page faults, and whatever algorithms I want to look at, and see which one comes closest to optimal. Okay? All right. So what we're looking at here then is what is kind of the best we can do. And the best we can do is, if we know what pages are coming, we know which ones to swap out. So here, when I have page 5 coming in, to get back to this example, when I have page 5 coming in, I look ahead then, and again, I see that 3 is going to be used in the near future. I'm looking for 1, 2, or 3. 3 is going to be used. Then 1 is going to be used, but I don't see where page 2 is going to be used. So I would decide to swap out page 2. So again, page 1 is going to remain. Page 5 is going to come in where page 2 was, and page 3 will remain. Because my choices were 1, 2, and 3, and I looked, and 3 and 1 were going to be used before page 2, so I swapped out page 2. And that was another page fault. Now when I get to the next page to come in, or the next page that's needed, I should say, it's page 3. Page 3 is already in memory, so I don't have to do anything. There's no page faults here. But now when I get to page 4 being needed in memory, I look ahead again. And I say, okay, which ones are being used next? I look ahead and I see, oh, 1's being used, and 5's being used, but 3 is being used later than that, so we remove 3. Okay, so I think you guys have the algorithm now. You can continue and fill out the rest of this chart, and then you understand how the optimal page replacement algorithm works. Any questions? Okay, let's look at one more, and that's the LRU page replacement. And now we want to replace the pages that have not been used for the longest period of time. So again, we're going to start out putting page 7 in memory, and then 7 and 2 will be in memory, and then 7, 2, and 3 will be in memory. Okay, and each of those, of course, since they weren't in memory and we had to bring them in, each of those caused a page fault. So that was a page fault, that was a page fault, that was a page fault. Okay, now with least recently used, we now look at which page has not been used for the longest period of time. Well, if we look here, we used page 7, and then we used page 2, and then we used page 3, and so 7 wasn't used most recently. So again, we're going to replace page 7. And Hala, you're ahead of me here. So we're going to replace page 7 with a 1. 2 and 3 will remain in memory, and that caused a page fault. Now when 2 is ready to be used again, we don't have to do anything because those pages already remain in memory, so we don't have any page faults here. So they're going to remain in memory. And then we go on to page 5, needing to be in memory. So when page 5 needs to be in memory, what was the most recently used? Now, you can see here where this is different from FIFO, because even though 2's been in memory the longest, it was just used in the previous iteration. Okay, so we already used 2 just recently. We used 2 right here. Right before that, we used page 1, and right before that, we used page 3. So the least recently used, the one that hasn't been used for the longest amount of time, or Reef, you're exactly right, page 3. So that's the one that we're going to replace. So we'll put page 5 in where page 3 was, and 1 and 2 remain in memory. Okay. Unfortunately, the next page to come in is page 3, which we just swapped out, and that's unfortunate, but it hadn't been used for a long time, so we swapped it out. So now which page are we going to use? We look back and see which ones we had used most recently, and we see that we used 2, we used 5, and then we used 2, and then we used 1. So which one is going to be swapped out for 3? Well, Reef, you got it right. It's going to be page 1 will get swapped out. And again, that's going to cause a page fault. Okay? So again, I think you can go through the remainder of these and figure out the rest of this chart that's telling us how many page faults each of these use. Okay, and that's pretty much, a lot of what the programming assignment is going to be is what we just talked about. What we just did is figuring out how to do that in Java, how to write the code to do that. So it's really important that you understand these algorithms and how they work, because you're going to be writing them in your next programming assignment. Are there any questions? Now, like I said, you all should have received these charts so you can fill them out and count the number of page faults. And tomorrow I will send you these slides, and in these slides I'll include the answer. Okay, so you'll be able to look at my answer and compare it to yours and see that you got the rest of the chart right and you counted the right number of page faults. Okay. Amjad, do you have a question? Okay, you're welcome. I have a few more slides that I can go through here, but it's mostly information that's in your book, the other page replacement algorithms. And again, you're going to be talking about the most frequently used one. And again, I think now that you know the least recently used, you can figure out how the most frequently used one works for your homework assignment. There are other things that are done using reference bits, and so if something has been referenced very recently, you're not going to replace it in a FIFO algorithm, you'll wait, and so forth. And your book goes through these in detail. Frame allocation, again, this is something that, you know, like we have to replace pages in memory, we also have to replace frames on disk, and that talks about doing that. And part of the problem when you're replacing frames is that sometimes page faults are happening over and over and over, and your process gets into what's called thrashing. Kernel memory management, again, what we're talking about during this class so far has been user memory management, and kernel memory management is different, and your book talks about that as well. So I didn't really get a chance to go through those in any detail, but again, all that is in your book. Okay, Amjad, you're asking me about the midterm and the midterm exam. And delaying the submission. Yeah, here again, you know, the problem is once you take your exam, we're right into week 9 right after that. And so I will take a look at it. I know you need to study for the midterms, and you're taking more classes than just this one. So let me take a look at the assignments that are coming up. Again, we still have a couple weeks till midterms. You should be able to get your homework done for week 6, and we can talk about week 7. Okay. The problem is, Amjad, we only have so much time in this course, and so many things that need to be covered. So you know, it's either you do it now, and it helps you actually to do the work for week 7 and week 6 before the midterm, because that material is going to be on the midterm. And so the more you look at what you need in week 6 and week 7, the better you're going to do on the midterm. Okay. Yes, you need to study for all your subjects. I'm aware of all this, but the schedule is set, and there's not much I can do about it. I will certainly look at your assignments and you know, keep it under consideration that you do have midterms and so forth coming up, and I'll get back to you. Okay. As far as studying for the midterm, what I've been told, again, I sent you the email yesterday, is that the midterm is being developed, that we are supposed to get study guides for the midterm that I will give to you as soon as I get it. And you know, if you have any questions, if you're reading through the materials and not understanding things, I will certainly answer any questions that you have. But to be totally honest with you, I do not know what's on the midterm at this point. I have not been given the midterm exam, so I have no idea. Okay, we're waiting about week 7 homework. What I was told, as far as week 7, let's see, week 7 is actually due before the midterms start, or actually right when the midterms start. When we get into week 7, Amjad, I'll look at the assignments, and if we need to modify the due dates, I will do it at that time. Okay? Let's not worry about it this week. Let's just worry about week 6 for now and see how things go. Okay? But I will be flexible on that. Okay? So don't stress out about week 7 yet. Okay? Hala asked if there is programming on the exam. Again, Hala, the only thing I was told is that the exam will be a combination of multiple choice questions and short answer. Now that might mean that you have to write a line of code, look at some code, and answer a simple question about it, you know, a one-line answer about the code. But like I said, I haven't seen it. I cannot tell you one way or the other what's on it. Okay? So as soon as I get that information, I promise you I will get it to you as soon as I can. But I don't have any information. We keep asking for it, and we haven't gotten it. Okay? There was a rumor that one of the Franklin professors was writing an exam. I'm looking into that as well. What I was told is that none of the Franklin professors should be writing their own exams, so I don't really know why that person was doing that. But I'm looking into that as well. As soon as I have answers, I'll pass them along. Okay? So again, work on these different page replacement algorithms. That's going to help you in the programming assignment. It'll also help you understand the homework for this week. And I will actually be sending you the slides that will include a slide with the answers for each of these so that you can just see if you got it right, or see if I got it wrong, just in case my answer isn't right. But I think mine's right. We'll see. But that's all I have for today. If you have any questions, please feel free to email me, to post questions on the discussion board, and so forth. And again, I will get you any information about the midterm as soon as I get it. You're welcome, Sahar. You're welcome, Hala. Everybody's welcome. This is my job. This is what I do. So have a good rest of the evening, and if you have any questions, let me know, and once I get any information on the midterm, I'll pass it along, and then if there's any way I can help you review things, I can help you with that as well. All right? Have a good evening. Oh, I'm sorry that you're afraid for midterms. Actually, when I give a midterm in a face-to-face class where I'm with my students, I am so nervous for them that sometimes my hand is physically shaking when I hand out the midterms, because I want them to do a good job, and I get so nervous for them. So. Okay, I'm going to stop the recording now if there are no other questions.